Okay, sorry. Okay, so today we will study LED, light emitting diodes, for the diodes and solar cells. So these are a very simple concept, a very simple, the design of this circuit is not that easy. I mean, the design of the cell and all, it involves certain complicated procedure, but the principle behind all these things is quite simple. So, like the Zener diode we have discussed before, light emitting diode is also another special type of diode. It is special in the sense that in light emitting diodes, we are going to use a special type of semiconductors known as direct band gap semiconductors. So far, I think we have already discussed about silicon, germanium, all those elemental semiconductors. These are called elemental semiconductors. Elemental semiconductors. So all these elemental semiconductors, they usually have what is called indirect band gap. So what is an indirect band gap? When we consider actual semiconductors, actual materials, the E versus K energy versus K curve is what determines the property of the material. Like we discussed at the beginning also, we have seen that in the energy band concept, we have talked about energy, and we just write that this is conduction band, empty band. We just write that the topmost filled band is called the valence band, where the valence electrons, which are participating in covalent bondings or any other kind of bondings, are lying in this valence band, right? Now, this particular plot, this is just a simplest representation of energy band diagram concept, and uh, in uh, in this figure also, we talk, this is this exists is your energy. So the top side is this empty band is called your conduction band, and this is your valence band. So the field energy bands are called valence band. And when you are writing energy band diagram, I mean this kind of thing, here you see that this is the space, this is the x-axis. Also, often we talk about depletion layer also, depletion width also, right? We also talk about the depletion width. Where is that our depletion width calculation? Let me just go back. Yeah. All right. I think that is too far away. Anyway, uh, in the depletion width calculation also, we usually plot in terms of E versus distance, like this. See, this is our boundary between P type and N type, and this is we call it 0, and we call this x1, and we call this x2, and yeah, there we calculate the depletion with X and all. Yeah, that is the material. Sorry, I just confused with the energy band here. Anyway, so what I'm trying to say here is that the on the left side there is this thing P type. On the right side there is a N type, and there is a depletion region. So the depletion region is here. The depletion region is here. This is your depletion region. So this side is the N type, this side is the P type, and you have a depletion region, right? But when we study the electronic band structure of actual material, this is the kind of simplified band structure we can have. Like in a silicon and germanium and all these elemental semiconductors, the band gap, that is the energy gap between, this is your valence band, this is your valence band. So the valence band lines, they are never a flat line, so they are this kind of curve and all. So this is the valence band, this is the top of the valence band, and the conduction band also in actual material, it is never like the flood line that we usually represent. So in the E versus K diagram, the conduction band is also having a certain band lines like this. So this is the bottom of the conduction band. This is the top of the conduction band. So the energy gap between the bottom of conduction band and the top of valence band is what is known as the energy gap. So what is known as the energy gap? The bottom of conduction band and the top of the valence band. So they usually involve band lines which are not flat lines, which are curved lines. When you plot energy versus K diagram, K is the momentum wave vector 2.2 pi upon lambda. Okay, the reciprocal space K vector that we already study in your solid state. Now, in silicon and germanium, uh, in order to have a transition from the valence band to the conduction band, you need a certain change in K. So it has to be associated with change in momentum or change in the K vector. So the K value here is, let's say K1, the K value here is, let's say K2. You need to have K2 minus K1. So there has to be a change in this wave vector K value, a change in your, this is also called momentum, okay, because your momentum is, according to quantum mechanics, it's H cross K only. So change in K or change in K value is needed here in order to undergo electronic transition between the top of the valence band and the conduction band. So because of this, like unless there is a lattice vibrational energy, which can change the K value, which alters the K value, unless there is a lattice vibration which alters the K value, the transition from the valence band to the conduction band or the conduction band to the valence band does not involve emission of light or absorption of light. So I think I'm making it a little bit more complicated, but what I want you to understand here is that in the actual material science, in the actual semiconductors also, when you plot energy versus K, when you plot energy in the reciprocal space, the K space, the band lines corresponding to the valence band and the conduction band, they are never a flat line. So they are always a curve like this. So the top of this valence band is here. The bottom of conduction band is here. And in order to have electron transition from the top of the valence band to the bottom of the conduction band, not only that, it requires this much energy to jump up, but also it has to be associated with change in K value. Change in K value. Change in K value can only occur when you have a lattice vibration or thermal energy. So thermal energy is always associated with this thing, these transitions. So because of that, uh, uh, transition from top of the valence band to the conduction band or transition from conduction band to the valence band here, it cannot involve emission or absorption of light. Even if you are going to have a transition from the bottom of conduction band to the valence band here, because of the change in this thing, there will be thermal energy emission. So instead of having a light emission, it will result in thermal energy emission. So when you consider normal silicon, which which are usually used in which are usually used in our electronic devices, normal semiconductors, p-n junction diodes and all, uh, like normal semiconductor p-n junction diodes is mostly used in rectifier circuits and all these circuits that we have discussed before, like the Zener diodes also. Normal semiconductors like silicon base and germanium base are used. So when such elemental semiconductors are used, the transition from the conduction band to the valence band to the conduction band, they cannot involve emission or absorption of light because of the thermal energy associated with it. That is the requirement to have a change in K value. So let us put it like that. Yeah. So there are like certain detailed ideas, detailed description about all these things, but let's skip that for now. Now, however, when we are going for compound semiconductors like gallium arsenide, also cadmium telluride, there are many compound semiconductors. Depending in most of the compound semiconductors, we have what is called direct band gap. What is a direct band gap? Direct band gap is when the top of the valence band, this is the valence band curve, this is the conduction band curve, the top of the valence band and the bottom of conduction band, they lie at the same K value. They lie at the same K value. So when you are having energy band diagram, energy band structure like this, at the same K value, the top of the valence band and the bottom of the conduction band are located. So when such is the case, if you have electrons here at the top of the valence, the bottom of the conduction band, and suppose you have a vacancy here at the top of the whole valence band. So under such condition, electron from the bottom of conduction band can drop down or fall down to the top of this valence band. So when it falls down to the top of this valence band, since thermal energy is not required to see the K value, when there is a transition from the bottom of conduction band to the top of the valence band, empty space here, it will involve radiation of light. So light energy radiation is involved in this case. So in all semiconductors, light energy radiation will be, in all direct semiconductors, light energy radiation will be involved when you have electrons falling from the bottom of conduction band to top of the valence band. Like in gallium arsenide, the band gap may be something like 1.2, but in cadmium telluride, the band gap could be around 1.1. And there are certain other direct band gap semiconductors also. Zinc selenide, for example, the band gap is around 2.2 electron volt. And there are certain other things like other semiconductors like cadmium selenide. Cadmium selenide has a band gap of around energy band gap of around 1.8 electron volt. Okay. So depending on the energy band gap here, the light radiation emitted out of this transition will have different kinds of color. So I think we might have already seen an LEDs. Some LEDs like imaging diodes and all, they will display red color. Some of them will display blue. Some of them will display yellow, green, orange, and even white light. Right. So the reason here is that depending on the material, the direct band gap material you use for designing this light emitting diodes, you can have different colors of radiation. If the energy is large, let's say 2.4, 2.5, it will be in the violet region. If the energy is very low, let's say 1.1, 1.2 and all, the light emitted radiation will become reddish. Okay, so depending on that, depending on the energy band gap of this direct band gap material, you can design a diode which can emit several colors of light. Right. So how it is emitting is the process similar to the process which I have just described. Here, the circuit symbol for LED is The circuit symbol for LED is this. See at the bottom, this is the LED. So this is also the usual circuit symbol for an LED. So an LED, as you see, the connection is positive terminal of the battery is connected to P type, negative is connected to N type. That means light emitting diodes is connected in forward bias. So when you have a forward bias connection in these light emitting diodes, so the diodes here now is made up of what is called direct semiconductors, like all these things, either gallium arsenide, cadmium telluride, cadmium selenide, zinc selenide, cadmium sulfide, zinc sulfide. There are various direct band gap semiconductors, compound semiconductors. Let mute, mute.
Model veng ada lo ni masa mino lemaro.
Okay, so when we use such direct band gap semiconductors for designing this P and N junction here, PN junction diode, you will have this kind of band structure. I mean, this kind of structure, energy band diagram. Here on the N side, you will have large quantity of free electrons. Those free electrons are lying in the conduction band. We know that already we discussed. On the P side, we have large quantity of holes. We have large quantity of holes here at the valence band. Holes are lying within the valence band that we have already explained. So on the P side, we have plenty of holes lying on the valence band. On the N side, we have plenty of free electrons lying on the conduction band. So when you connect this diode under forward bias here, electrons from the N side will be injected towards the junction. Holes from the P side will be injected towards the junction. So when electrons arrive in the junction and holes arrive in the junction, what happens is that free electrons which are in the conduction band will find an empty valence band, which is called vacancy or holes here. So when you have electrons and holes within this depletion region, electrons will recombine with holes. So under this recombination, it will emit light radiation. So from the depletion region, it will emit light radiation. Under forward bias, electrons are injected in the depletion region. Under forward bias, holes are also injected in the depletion region, and electrons and holes recombination will occur. The recombination process will now involve emission of light if we use a direct band gap material. Okay, so in the normal silicon based semiconductor diode, which is used for rectifier and Zener diode, light emission cannot occur even if you perform a forward biasing. The reason is that they are in direct band gap semiconductor. Indirect band gap semiconductor cannot emit light because the transition from conduction band minima to the valence band maxima will have to involve thermal energy that will change the K value, that will change the K value. So as it involves thermal energy, it cannot result in emission of light in your normal silicon based diode. But if we make a diode using this direct band gap material, as you see, under forward bias, electrons and holes will recombine within the depletion layer, and that recombination of electrons and holes will involve dropping or falling down of electrons from the conduction band to the valence band, empty space here, the valence band, empty space. Then it will undergo light emission. So which color of light is emitted? That will be determined by the energy band gap. Who is giving me this? Oh, from the office. Okay, these are the mark sheets. I see. Okay, I got it. Okay, so did you Did you apply for that vendorship?
Yes, sir, I just did.
Okay.
But I'm not sure how that sir contacted them last time. But I don't know what they reply.
So the sanction was in the PFMS account or in the PFMS? That
I don't know.
you don't know.
Yeah, sir, they do not.
So I think if you ask RDPR, in that RDPR sanction letter, account number will be written there. So from that account number, we will know whether that is in the mission bank, non PFMS, or in the college bank PFMS.
Okay.
If it is in the college bank account, it will be PFMS, and your money can be disbursed only through PFMS.
Okay. Oh,
Okay.
I'll just
Yeah, ask him about the account, whether it's a mission bank branch or college bank branch. Okay. So, yeah, when depending on the choice of your semiconductor, whether you are choosing the gallium arsenide, cadmium telluride, cadmium selenide, or any other semiconductors, compound semiconductors which are having a direct band gap, you can have a diode which will emit the color of your choice, which will emit light radiation, the color of your choice. All right. So nowadays LED is now used in display devices like for example, now I'm using a touchscreen laptop, and here also they are using light emitting diodes, LED display. So from my screen, I can see various kind of colors, sometimes red color, everything, right? So in all this LED display, in one particular display unit, one particular pixel, there will be different colors of light, like different 3-4 LEDs. The combination of you know that there are certain primary colors. So I think for every pixel element, there will be uh, light emitting diodes which can emit all those primary colors. So depending on the combination of all those primary colors, I can see various colors of screen on my laptop, various colors of light on my laptop screen. So it is a very important technological advancement which is achieved with the discovery of all these direct bandgap semiconductors, right? Direct bandgap semiconductors. Now, photodiode is also another special type of diode where direct bandgap is again used. Direct bandgap semiconductor is again used. Okay, so in photodiode, instead of emitting light, we are connecting the photodiode in what is called reverse bias. Okay. When you connect a photodiode in reverse bias like this, here this is N-type. N-type is connected to the positive terminal, as you see, and P-type is connected to the negative terminal, as you see. So this is under reverse bias. So when you connect under reverse bias, without any light, in the absence of all this incident radiation, you know that under reverse bias, whether it's a direct bandgap semiconductors or indirect bandgap semiconductors, which is used for making this diode, unless and until the reverse breakdown is attained, the current is usually very, very small. Okay, the current is usually in microampere that we have talked about. And this microampere current is what we have said it as the reverse saturation current. Reverse saturation current. And we have put a minus sign in the reverse saturation current because the current direction is reverse to the direction of current under forward bias. So this is the forward regime. So under forward bias, it was something like this. The current was positive under forward bias. Under reverse bias, the current was negative. That we have said several times already. So in the absence of any light emission, the current will be very small, some microampere, unless and until you achieve a voltage breakdown. If you use a normal silicon semiconductors, if you use a normal silicon semiconductor diodes and shine light on it, it will not alter the current. The current will remain this few microampere current due to the reverse saturation current. But instead of using a normal silicon based diode. Suppose you are having a diode which is made up of direct band gap semiconductors. Okay, direct band gap semiconductors. So if your semiconductor that constitutes or that makes your diode is direct band gap material, when you shine light on it, what will happen is that, suppose you know that like this is the depletion region, this is p type, this is n type, and p type we have plenty of holes, we already know it, and in n type we have plenty of electrons, and then we connect them in reverse bias. Reverse bias means p type is connect with negative, n type is connect with positive. So when you connect the reverse bias configuration like this, plenty of free electrons in n type, and this is the depletion region. In the depletion region, there are like acceptor IO, there are silicon atoms, as well as on the n side there are acceptor atoms like gallium, aluminum, or whatever, plenty of silicon atoms and some amount of gallium atoms. On the n side, if you are doing a doping with let's say arsenic atom, you will have pentavalent arsenic atoms as well as some amount of silicon atoms also, some amount of silicon atoms and some amount of arsenic atoms like this. So the depletion region will be making made up of silicon atoms as well as arsenic atoms, pentavalent atoms on the n side, and here on the p side, silicon atoms as well as some amount of dopant atom like gallium atoms, trivalent atoms. Now when you shine light on it, light energy will be absorbed by this silicon based material, and as they absorb, let's say this is your indirect band gap silicon. As they absorb light energy from this, the electrons which are in the conduction band, valence band, they will absorb light energy, and because of that light absorption, let's say they jump up for some time, but as they do not find any energy states, no energy states is available here. As there is no energy states available here, it will fall down. So it will not involve electron transition from top of the valence band to the conduction band. This will not occur in the case of this indirect band gap material. Now instead of that, suppose you are using your cadmium selenide here, CdSe, and you are using, let's say, cadmium telluride here. Both of these are direct band gap materials. Direct. Okay. Now there are certain cadmium selenide atoms and cadmium telluride atoms, and these are the depletion region of direct band gap material. So in such case, when you shine light on it, this is the top of the valence band, this is the bottom of the conduction band. When light radiation is given to these electrons here from the top of the valence band, these electrons, when it absorbs this light radiation, if light radiation energy H nu, this is the band gap Eg, if H nu, the light radiation energy, is greater than the band gap Eg, then the electrons will gain sufficient energy to jump to the conduction band. So when the electron jumps to the conduction band, when the light radiation energy H nu is greater than the band gap, direct band gap here, it will result in electron as well as hole, electron hole pair formation. It will result in electron hole pair formation. So electron hole pair formation will occur in the depletion region when you shine light on it, electron hole pair formation. Okay. Now, when electron hole pair formation occurs, like you know that this side is p side, this side is n side. For example, on the p side, there are majority holes and few minority electrons. So the reverse saturation current IS, the one we often talk about, was the electrical conduction due to these minority electrons. So electrons transferring to the n side here, electrons transferring to the n side under reverse bias, minority electrons. So minority electrons and minority holes result in reverse saturation current. This. Now, under light illumination here, when we are using a direct band gap material, there is a electron, when the light radiation energy is greater than the band gap, electron from the valence band top will jump to the conduction band minima after absorbing light radiation. And that results in electron hole pair formation. So electron hole pair formation will take place due to light radiation. Due to light radiation absorption, electron hole pair formation will take place. So here you will find that when electron and holes are formed under reverse bias, in the those electrons which are formed in the depletion region will also travel towards the inside under reverse bias. So electron and hole pair are formed, electrons are traveling towards the inside. And under reverse bias, we know that the electrical conduction was partly due to the minority holes from the n side traveling to this p side. So when you generate electron hole pair in the depletion region, and due to absorption of light radiation, these extra holes also will add to the hole current. Extra holes which are formed in this process, that is absorption of light radiation and the subsequent formation of electron hole pair in the depletion region, they will also contribute to the reverse saturation current. So due to light radiation, you can generate certain amount of electrons and hole pairs, and the electrons and hole pairs which are generated due to light radiation absorption will add to the already existing saturation current, reverse saturation current, because they will flow in the same direction as the minority charge carriers. So if you listen to what I've been discussing carefully, you will understand that the minority free electrons from the p side and the minority holes from the n side, they are the ones which contributes to the reverse saturation current. The reverse saturation current is actually a very, very small current like the one we discuss here. Right. So when we have a p-n junction made up of direct band gap semiconductors, and when you have a light radiation illuminating the direct band gap semiconductor, these light radiations will be absorbed by these direct band gap semiconductors. In absorbing light radiation, electrons from the top of the valence band will jump to the bottom of the conduction band, thereby forming electron hole pair. So when free electrons and holes are formed due to the light absorption, these free electrons, they will move under the action of reverse bias. This side is negative, this side is positive, remember. So they will move under the action of this reverse bias, and the direction of flow of these electrons will be same as the reverse saturation current. So they will increase the current in the reverse direction. And similarly, the holes which are formed in the depletion region under the action of this biasing, they will also move along the same direction as the minority holes which are moving from the n side to the p side. Holes, due to electron hole pair formation, they also move towards the p side, and they will further add to the already existing reverse saturation current. So the current along the reverse direction, that is the negative current, will be increased depending on the light absorption. If the intensity of light is increased, then you will have more number of photons bombarding the semiconductors. So when you increase the intensity of light, you will have more number of photons falling on the depletion region. If more number of light radiations, more number of photons are absorbed, then you will have more number of electron hole pair formation. More number of electron hole pairs will be formed. large quantity of electrons and hole pair will be formed. So when you have large quantity of electron hole pair formed across the p-n junction here, again, under the action of this reverse bias, these free electrons will move towards the inside, holes will move towards the p side, and it will further add to the reverse current or the negative current. Thus, you can see that when you have a p-n junction diode made up of direct bandgap semiconductor, they can readily absorb light, and under the action of light absorption, the current across the p-n junction will be significantly increased, like the one shown here. So the reverse current can jump from few microampere to 100 microampere, can jump to 200 microampere, can jump to 300, 400, it can jump to 500 microampere. And if the intensity of light is further increased, it may increase up to certain milliampere current. Right. So this type of semiconductors, which are made up of direct bandgap semiconductor, and when they are connected in reverse bias and illuminated with light radiation, it can significantly alter the reverse current, the current passing to the diode in the reverse direction. Okay, so these kind of diodes are called photodiodes. Photodiodes are used as a detector in many scientific instruments, because this photodiode can absorb even a very small, a very weak, a very faint amount of light. Even if you have a very faint amount of light, means very low intensity light, this photodiode can easily detect. So it can